All right, welcome everyone to the Data Science Seminar Series from the University of Washington's eScience Institute. As part of the University of Washington, we acknowledge the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. Joining us today is Dr. Zhiang Chen. Zhiang is a postdoctoral research scholar at the School of Earth and Space Exploration at Arizona State University. He conducts research in automated geoscience, where he develops robotics and machine learning technologies for geosciences, focusing on seismic hazard analysis, geomorphology, disaster assessment, and environmental monitoring. We are looking forward to Zhiang's talk, and I would like to invite him now to share with us some highlights from his research. The title of his talk today is Automated Geoscience with Robotics and Machine Learning, a New Hammer of Rock Mapping, Detection, and Dynamics Analysis. As usual, please use the Q&A box in the bottom of your Zoom window to ask questions, and we will have some time to address these at the end of the presentation. So Zhiang, welcome, and we invite you to begin your talk.
Yeah, thank you, Anthony, for the introduction. Also, thank you for having me for the presentation. And today I'm going to talk about automated geoscience from my dissertation research. So what is automated geoscience? Automated geoscience is the practice of geoscientific research that leverages robotics for data collection and machine learning for data processing, such that the geoscientists are released from labor-intensive activities to focus on high-level cognitive tasks, including scientific observation, hypothesis development, and experiment design. And using robots for data collection is not new, either is using machine learning for data processing. However, automated geoscience really highlights the roles and the relationship of robots, machine learning, and geoscientists in a scientific method. So first, let's look at the conventional scientific method of geoscience. Scientific method was brought up by Isaac Newton and further developed by William Hill. In the loop of scientific method of geoscience, we have geoscientific observations, and we bring up questions, we form hypotheses, and conduct the experiment design, data collection, data processing. If we get the luck, we will form general theories, and then we apply these theories to have more broader applications or predict futures. All these tasks have to be done by people. And if you recall the definition of automated geoscience, it perfectly fits the framework of scientific method. So automated geoscience leverages robots for data collection and machine learning for data processing, such that geologists can focus on tasks which require more creativity and higher order cognition. One advantage of automated geoscience, because robotic data collection provides a large amount of data, and it allows us to have transition from deterministic modeling to probabilistic modeling. And also, because conventional data processing may involve cognitive bias, because different people may have different data interpolation. And when we are using machine learning to process data, we are trying to eliminate the cognitive bias. Okay. And the method starts from geoscientific observation, but what if geoscientific observations are not accessible or interpretable? This seems a very abstract question, but it actually is quite common. Before Mars rovers, close-range observation is not accessible, and sites and volcanoes or deep oceans are not easily accessible. And nowadays, we have a large amount of data, like data from sensor networks, mobile robots, satellites. There are just too much data for us to interpolate. In this case, how can we make geoscientific observations? So automated geoscience propose to use robots to gain access and use machine learning to interpolate data. Based on this idea, we have general form of automated geoscience. So with the availability of advanced hardware and computing, there are more exploration-driven research. Sometimes we have to explore more at the beginning and collect more information, then we can ask the correct or proper question. So automated geoscience is not just about the automation of some tasks. It highlights the roles between automation and geoscientists. It is the methodology of doing research. So one demonstration of automated geoscience from my research is the study of photoscarp. Photoscarps are surface expression of faulting. And during my PhD research, I had opportunity to look at rocky photoscarps, which are intermediate between production limited and the transport limited photoscarps. And we are interested in the formation of rocky photoscarp. As you can see, there are many boulders on photoscarp, and we are also interested in seeing the correlation between those rock distributions and the rocky photoscarp formation. So there are three major steps in the formation of rocky photoscarp. Initial cooling of extrusive volcanic rocks forms columnar joints, which are those large blocks. And we refer this process as volcanic cooling. And the second process is tectonic faulting. It offsets the columnar joints and exposes these large blocks to the surface. And those large blocks are visible in fields. Because of ground motion and chemical weathering, those large blocks might be toppled and fracturing into small pieces. We call the last process as geomorphic fracturing. And our hypothesis is that rock size distributions reflect the processes of rocky photoscarp development. If we really generalize our idea, it's not just about rock size. Rocks are everywhere, and rock size is just one of the geometric characteristics. For example, if we can extract a mask from a 2D image, we can get equivalent area and calculate effective diameter, and also convert the effective diameter to grain size phi, which is commonly used in granulometry. And also, we can fit the 2D mask with ellipse, and then we can use eccentricity to represent rock roundness, and use the major axis to represent rock orientation. The challenge here is how to extract a large number of rock masks. If we can get a large number of rock masks, then we can get the rock size, rock trait distributions. So here we present a 2D rock detection pipeline. We have piloted aircraft system to collect aerial imagery on photoscarp, and structure from motion is used to produce ortho map and digital elevation models. And we use a machine learning model, mass Gaussian, to detect and segment individual rocks. We have a bunch of post-processing to create a semantic map. If you are familiar with GIS, and you can consider a semantic map is a shape file with that is composed of a large number of polygon vectors. Each polygon vector represents rock outline. Here, because the pipeline involves a deep learning model, and we cannot input the entire map into the deep learning model because it requires too much GPU memory. What we do is we split a map to image tiles, and we also split annotation map to annotation tiles. And then we run our deep learning model on the image tiles and the annotation tiles and produce prediction tiles. From the prediction tiles, we mosaic the prediction instances to get a prediction map. Thus, there are two major challenges. The first one is to split annotation map to annotation tiles. Second is how to mosaic prediction instances. Of course, you can have brute force solutions, but for large scale applications in remote sensing, we need efficient algorithms. And we present a bunch of algorithms to solve these two challenges. And these algorithms are efficient for large scale remote sensing applications. And we apply these 2D rock detection and 2D rock detection algorithms to a study area in volcanic tablelands near Eastern California. So on this 500 meters by 200 meters study area, there are more than 200,000 rocks on this area. And on the photoscarp segmentation, we detected more than 30,000 rocks. And we get the rock size, grain size distribution, and eccentricity distribution, and rock orientation distribution. And those heat maps show the rock distribution on the photoscarp and its surrounding flats. It's probably obvious that there are more larger boulders on the photoscarp area, but this is the first research that really quantify the rock size distributions on the photoscarp and its surrounding flats. We also have an opportunity to inspect how rock size change perpendicular to photoscarp trees. So from the hang ore to the foot ore, we can see the rock size increases. And those large rocks correspond to the large boulders on the foot ore. And a correlation analysis between rock size statistics and the photoscarp height, which is the distance between these. And we found higher photoscarp has more or has smaller median grain size, which correspond to those geomorphic fracturing, which kind of makes sense because when we have higher photoscarps, there are possibly being more geomorphic fracturing that cause those small rocks. And we also found the higher photoscarps, on higher photoscarps, there are larger, those large blocks. And which also makes sense because when we have more tectonic faulting, that cause a higher photoscarp, and those blocks on the foot ore will be more exposed to the surface. And we also use rock orientation distributions to inspect a particle transportation model. So because the median rock size is similar to the size of a football. If you can imagine, if we throw a football from the foot ore, and ideally, and the football will rotate along its major axis and end up with the orientation that is parallel to the photoscarp trace. And we use the rock orientation distribution and conduct some correlation analysis that kind of support this particle transportation model. And a quick summary before we move to next. So the 2D rock detection pipeline describes a process of experiment design, data collection, and data processing. And then we have 2D rock detection algorithms really focuses on two challenges in data processing. And then we use this pipeline and algorithms to solve a specific problem and studied the rocky photoscarp formation in volcanic tablelands. Remember that the methodology of automated geoscience is a loop, and my research so far has only explored one iteration, and with more iterations in future, we can improve the tools At the same time, possibly and hopefully we can generalize some theories to understand the photosculpture formation better. Methodology novelty is the introduce of rock trait distributions. So 2D rock traits enables statistic analysis. The deep learning model is not perfect. It may have false detections here and there, but if we can extract a large number of rocks to get rock trait distributions, and we have demonstrated that the effects of deep learning errors on rock trait statistics is very small. And 2D rock traits are good, but information is still lost by reducing one-dimensional information. Extracting 3D rock traits is the motivation of the second part of my dissertation research. And specifically, we are looking at precuriously balanced rocks, which is one type of fragile geological features. And precuriously balanced rocks are those freestanding boulders that are attached to, but not affixed to a pedestal. So if there is a strong earthquake, PBR or precuriously balanced rocks or PBR might be toppled. So PBRs are negative indicators of earthquake in nature. And there are many ways to describe how the fragility of a PBR, and one simple descriptor is the minimum contact angle. And for example, this is a PBR before earthquake, and after earthquake, when the PBR is toppled, and the minimum contact angle will increase. And why PBR is useful, and they are useful for seismic hazard analysis, because they can provide the existence of PBR can provide an upper bound of ground motion, which helps the civil engineers to decide sites for critical infrastructures. And this project is funded by Pacific Gas and Electric because they are interested in ground motion activities near their nuclear plants close to California coastline. Previous work only specifically look at one or several PBRs. And this work, we are thinking if we can get a large number of PBRs, and then we can, for example, we can build a distribution of minimum contact angle, and this distribution should be a better representation of fragility of that area. Because if we only look at one or several PBRs, the sampling might be biased. And then the engineering challenge here is how can we map and segment those PBRs? And then we present a workflow of PBR search, mapping, and analysis. So first we have an offboard 3D rock detection pipeline. We also started from UAS survey, collecting aerial imageries and the structural motion to generate orthogonal deck. We use the same 2D rock detection pipeline to detect the freestanding rocks on the site, and we use the bounding box to crop the bounding box of the 2D rock to crop the point clouds. And in each 3D box, we have points on the PBR and points on the pedestal. And then we have another deep learning model to segment the points on the PBR and the points on the pedestal. We can get a 3D version. We can get a semantic map, 3D version semantic map. And this offline 3D rock detection has advantage of rapid deployment. For example, if someone go to the field and quickly conduct the UAV survey, and then they go to the hotel, they send their data to me, and I can segment all the PBRs for them. And the next day, they can go to the field and verify the PBR, and maybe they will have more detailed mapping. However, it has a problem because the UAV survey is pre-programmed, and when the minimum contact angle is very small, the UAV might miss those basal information. And also, it's kind of a waste of computing and memory if the PBRs are sparsely distributed, because we don't want to map, we don't want to waste our computing and memory on those unrelated features. Thus, we come up with onboard 3D rock detection system, and we customize a hex rotor with 2 companion computers. The first one is in charge of trajectory planning, motion planning, state machine, and the other one is NVIDIA TX2. It has edge GPU, which enables real-time object detection, and it has 2 stereo camera. This is stereo camera. This stereo camera is used for 3D real-time mapping and also object detection. And this one is for visual initial odometry. And if you think about an offboard method, it kind of separates UAV survey and data processing. But for onboard methods, it integrates the machine learning and the UAV survey. So while the UAV is surveying, it has awareness of what object it is detecting. So it has so it can conduct more intelligent and agile trajectory to map more interest objects in a more efficient way. So first, the onboard 3D rock detection system first start with a long-more search from a high elevation. At the same time, it is using its stereo camera, one of the camera in the stereo camera to detect PBR in real time. And once a PBR is detected, it will move around because machine learning may has false detection. And this step is to eliminate the false detection from multiple different views. And once a PBR is verified, the drone will fly closer to the PBR and conduct a circular motion to map the full body of a PBR. And when the mapping is done, the drone will return to the no-more search pattern and find the next target. Once we can map PBRs, we need to understand its dynamics. There are 2 major applications of PBR dynamics. If we can, the first one is overturning, and we can use the overturning to study past hazard analysis. And the other one is large displacement, which is useful for rockfall prediction. And we will talk about that soon. For overturning studies, we can consider the dynamics as a function, and the input is ground motion. For example, we use peak ground velocity and peak ground acceleration, and we will see the overturning response of a PBR if a PBR is toppled or balanced. And here, the ground motion is a single pass cosine displacement. For example, if given ground motion here, and we want to see if a PBR is toppled or balanced after the ground motion. For large displacement study, and it's still, we can describe it using a function, but it's slightly different. Given the initial state of a PBR, for example, initial position, orientation, and velocity, and we know the trajectory, if we know the terrain model, and we will see, and the large displacement the trajectory can be phrased as a function of initial state. The way we are studying the PBR dynamics is to build a virtual shake robot. So the virtual shake robot is a shake table built in simulation. So it has a base and it has a linear rail, so which allows 1 degrees of freedom along this axis, and it has a pedestal and it has a PBR, and this pedestal can be replaced by realistic models that are mapped by UAV and structured by motion. And one innovation of this virtual shake robot it is built based on robotic knowledge and concepts. For example, we use a robot operating system to uh, for the control and perception system, and we use gazebo simulation toolbox and bullet physics engine. Yeah. So you can see we have a pool PBR here, and we are conducting the overturning experiment. So given one peak ground acceleration and peak ground velocity by peak ground acceleration, so those are ground motion parameters, and we will see the record response, overturning response of a PBR. First, we studied the relationship of fragility and PBR geometry. For example, if we compare B and C, so B and C, they have the same width but different height. So we will see taller PBRs, like PBR-C, is more fragile because you can see the boundary is closer to a smaller ground motion. And if we compare B and D, those two, they have the same height width ratio, but D is smaller in size. So a smaller PBR is more fragile. Also, like when they have the same height width ratio, but the other dimension is different, so that really doesn't really affect their fragility. And in nature, PBR, the geometry of PBR is not symmetric. So their ground motion response should also be asymmetric. Thus, we have those 12 parallel simulations to study PBR fragility and isotropy. So in these 12 parallel simulations, the PBRs are initialized with different orientations. And you can see even for opposite direction, their fragilities are slightly different. And for some scenario, like only when you can see the boundary is not smooth, it's not like a curve. And for this scenario, the ground motion has to be greater than some threshold, and PBR can be toppled. And we can also use the virtual shake robot to study PBR overturning from like the effect of natural support to the overturning. If you look at this here, because of the natural support, the PBR is not toppled. But if we remove the natural support, the same ground motion topple the PBR. And another beauty of virtual shake robot is that it provides a seamless tool for overturning and large displacement experiments. And those two experiments in geology are usually separately studied, but because they don't have a tool that can integrate these two, that provide the integration solution for those two experiments. And then we can record and get the more than 600 trajectories from different ground motions and study how trajectories change with peak ground acceleration. You can see larger PGA, the trajectories, the velocities are higher, and also the furthest trajectory is longer. And this is also reflected by correlation analysis. So a higher higher acceleration and higher velocity, peak ground acceleration and peak ground velocity results in larger mean terminal distance, which makes sense. So a quick summary, the overturning experiment provided an upper bound ground motion constraint. And one second, again, the existence of a PBR, and we know the PBR existence, and from the overturning experiment, we can get the upper bound ground motion constraint. And if we know the trajectory, and we can use large displacement to get a lower bound ground motion constraint. And if we can combine these lower bound and upper bound constraints, it can provide a better way for ground motion estimation. So simulation is good, but how do we know? How can we convince like geologists like this physics engine experiment and results is good? And that's we build a mini shake table for validation. And the mini shake table is open source and it has low cost, and it uses the same software system. It also uses ROS robot operating system, and then which guarantees it has the same control system because with the same control system between this physics and virtual physics shake table and the virtual shake table, and it guarantees they have consistent ground motion, which is important for validation. And the mini shake table provides reverse validation. That means we map the PBR and we 3D print, we downscale the PBR and we 3D printed PBR, and we conduct overturning experiment using the mini shake table. And then we reverse the 3D model in simulation and scale the size and same density and mass. And we kind of compare the result, the overturning results, physics engine between the physics and physics experiments and simulation experiments. And you can see they are very close. And we also notice that the difference, and we are still exploring the reasons. And also in future, the mini shake table can also be used to calibrate the parameters in simulation. So other translational applications of automated geoscience, one area that I'm particularly interested in is disaster assessment and response. We have sensor networks, drones, and satellites, and they can provide a large amount of multi-resolution post-disaster data. And then we can build a disaster decision support system, which can be used for search and rescue. For example, how can we use this information? How can we provide this information to robots and people for more efficient search and rescue? For example, one of the work during my PhD research is tornado damage assessment. We conducted a UAV survey and built a 3D model of a tornado after in Kansas, a EF3 scale tornado at Kansas. We built a 3D model, and we have machine deep learning to detect and assess the damage levels. And then we can build a high resolution damage map. And this is very important because it provides the damage information. Damage information can be used to study like tornado, the physical interaction between tornado and the structures. For example, in this case, we can kind of indicate, and also that's true, the tornado traces along this direction. And also this damage information can be used for search and rescue. For example, this area has severe damage, maybe for future work. When we have search and rescue strategy, we can probably prioritize those higher damage area. PBRs are common on Earth, And surprisingly, we also found them on Mars. So those photos are from Mars 2020 rover. And because PBR can provide upper bound ground motion, and we can integrate this with floating for better ground motion analysis estimation. And I'm also interested in carbon like environmental monitoring. For example, like understanding carbon distribution is important to study climate change. Most studies focus on effects of vegetations on carbon distribution. However, animals like wildlife may have indirect effects on carbon distribution. If we can use drones or some mobile robot platforms to map vegetations and map the distribution of wildlife, we can study the correlation of carbon distribution and wildlife distribution. So which can help us to understand how wildlife affect carbon distribution. And I'll end my presentation with this figure. I'm really excited about this research direction, which provides a way to push frontiers of robots, machine learning, and geoscience. And it's really the interface of these three that gives a powerful tool to potentially change the way of doing research. Thank you very much.
That's really fantastic, Zhiang. Thank you so much. Really interesting research, and thank you for sharing it with us today. We do have one question in the question and answers feed, which I'll read out and encourage any other participants to go ahead and type any questions you may have after hearing the talk today. So Zhiang, the question here is, what is the cost of the mapping device and who has access to use it? What is the scale or capacity of the mapping?
Yes, so we use various devices for mapping. We use commercial drones like DJI drones, and we also customize drones for specific tasks. As you can see, like those different offboard and onboard methods, they use different platforms. But compared to satellites, and those mobile platforms are relatively affordable. Like drones, only drone is about $2K, and it depends on what sensor you want to have. If you want to have like commercial camera, which is more affordable, but if you want to have multispectral camera like Maxens, and they are like $5,000. So it really depends on what sensor you want to have and your what mobile platforms you want. And for the scale, yeah, that's one thing. So if you think about this, let me show you this figure. So in future, we want to fuse the data from sensor network, drone, and satellites, and they have different resolution and scale. So sensor network, they are accurate, but they are not precise because we cannot distribute them everywhere. And there are like these gaps between these sensors, we don't have data. And for satellites, we have a large scale, but the resolution is not very good. And the drone provides information between these two. So, but at the same time, the scale is limited. Like the flight time for drone is 15 to 20 minutes. And so there are something we're trying to optimize. For example, we can improve the drone design, make it flight longer, like a VTOL, vertical takeoff and land. And those drones has higher flight time, and that means we have larger coverage. So I hope that kind of answer this question. But let me know if you have follow-up questions.
Yeah, I think you did a great job answering that. I'll give folks another few moments here if there are any other questions to type them into the question panel of Zoom. Just give people one last chance here. And I'm not seeing any additional questions. So I think, Zhiang, thank you again. That was really incredible work, and excited to see what comes next in your research. Thank you for sharing with us today, and we'll wrap up the webinar. And thank everyone for attending.